Thank you for the nice introduction. My name is Simon Bachhuber, and I would like to talk to you about our recent research on plug-and-play inertial motion tracking with sim-to-real transfer. And so let's start by explaining what is inertial motion tracking. So in inertial motion tracking, we try to estimate the motion of humans in space using inertial measurement units. That means that typically we attach one IMU in each segment of a person, and then we fuse the 3D gyroscope, magnetometer, and accelerometer to estimate the position and orientation of all the segments, and then thus we can recover the pose of the person, and then also capture it, for example, digitally, as it is shown here in the lower left figure. And recently, there have been three major directions in which IMT as a field advanced. And the first one is that we would like to achieve self-calibration. That means that the pose estimate of our algorithms should not depend on how the IMUs were attached on the segments. The second direction is, ideally, we would not have the requirement of really having one IMU per segment. If we could omit single IMUs on some segments, this would make it less complex, more comfortable for the end user, less costly, and so on. And then the last direction is we would like to not use magnetometers, because in indoor environments, the magnetic field is not as homogeneous as we might expect due to wires in the wall and metal materials. And so the goal is to have a solution that has all these three advances, which is currently not the case. And so here we, for the first time, achieve a problem formulation that does combine all these three things. So we consider three segments, and they are connected by two hinge joints here. And on both outer segments, but not on the inner segment, we have 260 IMUs. So that means we don't have magnetometers. And then the goal is to have a filter that, given those 260 IMU signals, recovers the pose of the chain, that is the quaternion from 2 to 1 and from 3 to 2. And also it should work independently of the length of the segments that are involved, and also of the placement of the IMU on the segments. And so how do we achieve this? Well, this is a machine learning-based approach. So first we propose an architecture which, if it works, if it's trained, it solves the problem. So that means that it takes a time series of measurements prior to a certain time point, and then it returns us the relative pose at that timestamp. And this is really a filter, so it's not time series to time series. It can be done on a per time step basis. And if we have trained this network, it then is a sparse 60 inertial motion tracking filter. And here at the bottom, there is the architecture, but it's not too important now. And so if we have a network, how is it trained? Where is the training data coming from? That's the probably most unconventional way of doing it. We only train in simulation. Because this is a rigid body setup, similar to the bones in a human, which are very rigid, we can train the network in simulation by having years of training data of kinematic chains randomly moving, and thus creating the IMU sensors. And because it's in simulation, we also have the ground truth pose measurements. But there is a catch. So we have now trained the RNNO with the RCMG, but it simply won't generalize this easily on experimental data, because we have only trained in simulation. And the point here is that we need forms of data augmentation to make this work. This concept of training in simulation, yet application in reality. Specifically, we need three particular augmentations, and we also show this in the paper, that if you omit only a single one, it no longer works. The first one is that we need range of motion restrictions such that segments are really solid objects that can simply move through one another. The second one is that when we do forward kinematics, the point of the floating base, so to speak, where the global orientation and position starts in the chain matters. You have to randomize across that point. So you have to choose it at different anchors. And then lastly, because we don't know the exact length in reality, we have to generalize over them such that the network is forced to implicitly estimate those parameters himself. So we create sequences from randomized geometries of the chain. So randomized lengths and positions of the IMUs. And so we have now trained the RNNO, and then we can now apply it to experimental data. So now onto the experimental validation. So what have we done first? We have 3D printed such a kinematic chain as we have seen in the problem formulation. And again, you can see in the orange boxes, the IMUs and the gray spheres are the optical motion capture markers, such that we have ground truth to compare ourselves to. And then we have recorded a sequence of continuous data of randomly moving that chain. And we also split it into many short sequences. And the long sequence we can use to just assess the stability of the estimator. And the short sequences we can use to assess the initial convergence. And yeah, you can see such motion. And the result is that this works really well. I'm sorry, the plots look a little bit not as I wanted them to look, but you can see it. Okay, that's unfortunate, but at the end result is that the tracking is really good, and it's after initial convergence. The RMSE is lower than 4 degrees, and we have also quite rapid initial convergence of about 2 seconds, because initially the network can't know the pose. So, but it's this convergence to the true estimate is quite fast. But this is nice, but recently we have also advanced in new directions. So we can really ask ourselves, how far can we push this? Because if we train in simulation, we can train on pretty much everything. And so we have first created a slightly new architecture for the network, because what was annoying to me is that I have to train the network on a specific number of segments. And ideally, I would like to have one pre-trained network that you can apply despite it being maybe 3 segments or 4 segments or even 5 segments, or even some branching in the kinematic chain. And so I have proposed a new architecture that allows for such a dynamic output. Because if you have 3 segments or 4 segments, the output dimension, the pose is different. So you have to have the ability to have a dynamic output despite having the same set of parameters. And then also we have recorded new validation data. And you can see it here at the bottom, for example, a part of the new chain, and it's now 5 segments long, and it has various joint types, not just hinge joints. And it also has on each segment 2 IMUs, one which is rigidly attached and one which is only attached via fold. Because in reality, IMUs are not perfectly rigidly attached to the body. Instead, they are often attached over the clothes, and so they also move. But you're still interested in reconstructing the pose of the person, not the motion of the clothes. So let's look at a video. So the first thing we consider now is, instead of just 3 segments, what if we just make it 4 segments? Now there really are 3 degrees of freedom between the 2 IMUs, and we still want to estimate everything that happens in between them, even though we have 0 information about that. And it also uses all these results that can now use the same pre-trained network. So let's look at the video. So this is only a rendering of the experimental data as the main view here. And the left, you can see actually the experimental trial, and on the right, you can see some bird's eye view. And then in the sort of blue color, you can see the prediction of the network, and the other is the ground truth pose. And you can see that the tracking is not perfect, but it's still already quite accurate. And then another direction we tried was, and of course there's also a plot of just looking at the angle errors over time. And yeah, initially they are quite off, as one would expect, but then over time they converge quite well. And then finally, what else we tried was, we again use the same pre-trained network, and we go back to only having 3 segments. But now we use the IMUs that are attached via foam that move. And what's interesting is that this works even though the network has never seen in training, never experienced the concept of non-perfectly rigidly attached IMUs. There's one big difference now. It still works, but the estimate jitters now. It's much more nervous. You can see that the blue estimate wiggles a little, but still it doesn't break. The estimate is still relatively accurate. It only jitters, and that's really good because that means when we include that, when we sort of force the network to learn, well, more aggressive low-pass filtering, in essence, then this will go away as well. I'm quite confident. And yeah, to conclude, here we really have achieved to train a single network in simulation, but yet applied in reality, and to solve IMT problems, and IMT problems that are sparse, that are magnetometer-free, that can self-calibrate, and that even works when the IMUs are not rigidly attached to the body. Yeah, that's it. And if you have any questions, please ask them.